Because we didn't look at this one, right? No. So what if we had the volume of an irregularly shaped object? Okay, so for that first object, okay, if we're mathematicians, we could go through and say, well, I can determine the volume of an oval that fits within that, and then I've got the volume of these triangles. I don't know why that one didn't look like a triangle, but whatever. And I could then add up the volume of all those pieces, and I would now have an approximate volume for the shape of that object. Okay? Phenomenal job, mathematicians. That's great. You were able to do that with a weird-looking object. How about the next one? How would you measure the volume of the crown? Right? That becomes a lot more difficult because what have we added? Space or volume, a third dimension. That third dimension makes our approximations, a la mathematics, a little bit more difficult. Right? If you are that good at mathematics where you could model that and come up with the volume of that using your mathematics skills, you're probably well beyond this class. Right? Since you're in this class, you probably can't do that. Right? If we take it a step further, and I know it's weird, but it's really hard to get a picture of this. What am I trying to get a picture of? The cloud. What's the cloud? Give me a gas. We're trying to get the volume of a gas. That also becomes equally difficult to kind of trap and calculate a volume of. So how could I potentially get those volumes easily? You did a lab on it.
Put it in water.
Okay, put it in water. We can measure that volume by displacement. Okay? So I can take a graduated cylinder where I know the volume marked out. If I put that irregularly shaped object into it, the water rises based off the volume of the object. So the difference in those volumes, and I now have the volume of the object. Right? Right. We could also do it with gases. Right? So in this case, what they're trying to show, I believe this was an image from the textbook, we have a bunch of crystals or something down in here. When those crystals get heated up, what do they produce? A gas. That gas fills up this tube. What happens when enough gas gets into this particle or into this container? It pushes down on the water. Well, then what happens? The water will go up the tube and collect out in this other beaker. If I have graduations on that beaker, I can now go through and look at a difference in the volume from when I didn't have the gas to when the gas was formed, and I can determine the volume of the gas. Kind of make sense? Right? Kind of neat. Right? There is a big issue with this experiment, as it's shown, that we kind of have to watch out for, that we'll see later in this unit, actually. Has anybody taken a balloon and heated it up? All right, so maybe one person. Has anybody seen those big balloony objects in the sky? Like the hot air balloons? So someone just drove around with this giant balloon on the back of their car? Okay, we'll get to that. How many of you have seen those balloons driving around on the back of someone's car? You all seen them in the sky. How come you haven't seen them on the ground? What do they look like on the ground? There's no air in them. They're just these shriveled up little balls. You could roll them up and put them on the back of a really big truck, but you can put them on the back of the truck. Okay? What happens to get them up into the sky? We don't fill them with gas. What do? We light a fire. We fill them with heat. What does the heat cause the air to do? To expand into the balloon, and now the balloon fills up. Okay, so heat will cause gas to move, which could cause the liquid to come across over here. So what am I measuring the volume of? Am I measuring the volume of the gas or of the heat? Okay, if I'm trying to measure the volume of the gas, I better make sure that heat is minimally affecting it. How can I make sure the heat minimally affects it? Why is the gas now minimally going to affect it? Or the heat?
It cools down everything.
as the gas comes out, it can now cool down so that by the time it gets to where I'm measuring it, I'm not measuring a temperature change, I'm only measuring the presence of that gas. Okay, so I want the heat source as far away from my detection source or my measuring source as much as possible to minimize the effect of heat on that change. Make sense? Okay. So, density. We said the conversions with density were important. The understanding of density wasn't for this exam. Which weighs more, a pound of lead or a pound of feathers? Okay. They're the same. Okay. It's a fun question to ask little kids because little kids usually go, oh, the pound of lead weighs more. And you go, ha, you're an idiot. That's not nice. Don't do that to little kids. Okay. They both weigh a pound. Why is the kid saying a pound of lead is heavier? Okay. There's all sorts of reasons behind it, but one of the arguments for why we end up misinterpreting that question could come back to density. Okay? We could think about it as being hit. Which one am I rather going to get hit by? Probably a pound of feathers. Why? They're less dense. Those feathers are spread over a larger area so that when I get hit with that pound of feathers, I'm displacing it over my whole body. Okay? But if I got hit with a pound of lead, that's probably coming in like a fist. That's hitting a very small area of my body. That's going to hurt a lot to have all that weight smash into me in that one point. Okay? That's potentially what's going on with why we have problems with that. Okay? So what we're looking at is a density. Okay? The relationship between the mass and the volume for an individual substance. Okay? It's not perfect, but most substances have different densities. Okay? And it depends how accurate you want to get in your measurement. And if you get super accurate, you can find out that, yeah, they all have different densities. Okay? And that's the relationship between the mass and the volume. Okay? Why are they different? What's the difference between hydrogen and helium?
Different properties.
True. Keep going. Be more specific. What's the difference between hydrogen and helium? What's that? Number of protons. What do protons define? Protons would define the element. So we're saying the element's different. Yes, but what else do protons contribute to? Mass. So if I look at hydrogen versus helium, helium weighs more. Okay, it has a larger mass. What happened to size as we moved across the periodic table? It decreases. Okay, so if I look at two hydrogen atoms and I put them near each other versus two helium atoms, which one takes up more volume? Hydrogen, because hydrogen was larger. So they have different masses and different volumes. When I go through to look at the ratio, I'm going to get a slightly different answer. Okay, so they have different masses and different volumes. Okay? So it's kind of a neat observation. We can tie that back to a physical property. Okay? What is then density? And for those of you that want to say mass over volume, fantastic. Give me a different answer. What is density? It's kind of a hard question. Okay, as a hint, miles per hour. It's the same thing. What is miles per hour? Miles per hour isn't quite a unit, actually.
It's a rate or ratio.
It's a ratio. Where might we use the ratios?
Conversion.
It's a conversion factor. Density is a conversion factor. Miles per hour allows me to relate what? Miles to hour. Distance to time. What does density allow me to do? Relate mass to volume. All it is a conversion factor. Okay, so I can use density as a way to convert or relate mass and volume for an individual substance. Okay, that's arguably not all that neat, but it's a conversion factor, okay, which you're responsible for being able to use according to the previous unit. Okay, so let's move a little bit further into kind of some concepts of it. What units might we expect for density? Well, what unit would you expect for mass? Grams. What unit might you expect for volume?
Milliliters.
Milliliters. Why?
Because water and liters. That's
What measurements do you typically make in lab? Metric system. Okay, so we picked metric system units. Why'd you pick grams? That's what our scale is. That's our core unit. What unit did you pick for volume? Milliliters. Is that our core unit? No. Why'd you pick milliliters? Most of our measurements measure by milliliters. Think about chemicals as being toxic. If you walked into lab and you had to measure things in liters, how many chemicals are you mixing? A lot. So you're exposing yourself now, theoretically, to lots and lots of toxins. Theoretically. Right? That would be dangerous. So what do? We scale it down so that we don't have to deal with as much substance at an individual time. That's why we look at milliliters. So when we're looking at our densities, we're typically looking at our easiest to measure mass and volume units. So grams and milliliters. Okay, what happens when I move to a liquid? Why is it the same thing? What would my solid look like? So let's draw a pen, work. Thank you. Here's my first solid particle. Where would my second solid particle be? Right next to it. And the next one? So on and so forth. Okay. I know I changed the size. Give me a break. Liquid. There's my first liquid. Where's the next one? Right next to it? A little bit more spaced. Okay, remember when we move up to a liquid, we're breaking some of those intermolecular forces, so we get a little bit more space. There's a little bit more movement, but not a lot. What happens when I move up to a gas? There's now a lot of space between those individual particles. Okay, is that going to make me want to change the unit? Okay. Well, as we move through from solid to liquid, okay, we aren't really changing the space all that much between the individual particles, which means what happens to the density? It doesn't change that much. I get the same mass per the same volume, ballpark. Okay, 0.9 versus 1. What happens when I move to a gas? Changes a lot. Now there's a massive distance in between those individual particles. So if I looked at the same volume, what's my mass going to be? A lot less. So I could potentially be looking at something on the order of grams. I'm completely making this number up, by the way. Okay. That's a lot of zeros. Maybe I don't like zeros, so I could write it in scientific notation, and I'd get 1 times -4. Why negative? Because it's a small number, right? Okay. How many of you like powers of 10? Okay. How many of you like negative powers of 10? Okay. Wow, so 2 people in the whole class. Interestingly enough, and it could be just that I didn't see, people liked negative powers of 10 but not powers of 10. That seems kind of weird, but that's just me. Okay? So if we can't deal with either the decimal value or the powers of 10, what do? We change the unit. We know our powers of 10 mean something. So I could change the unit. Instead of looking at grams, I could look at milligrams. That's going to change my interpretation, so I end up with a number that looks like all the other numbers, but because I've changed the unit, watch out for the holes. It's okay. We can change the unit to help us wrap our puny little human brains around it. Okay? And for those people that think, well, isn't that big a deal? Why do we really need to do that? Again, we have calculators. We probably don't need to do this anymore. Okay? But 100 years ago, our calculating ability wasn't so great, so that's why we invented these different units, so that we could get these numbers into something that makes sense. So this is where we could end up with dimensional analysis. So let's take a look at some examples. For the solids, what are the numbers for our solids? 1, 1, 1, 2, 7, 10, 20. Okay? That's kind of cool. All of those densities, we could count fingers and toes. Like, that isn't that bad. Okay? For liquids, a little bit less than 1, 1, 13. Again, fingers and toes. Easy to recognize, easy to manipulate. Take a look at the gases. Those are all the same numbers too. So wait, but I thought the density for gases, liquids, and solids would be different. Okay, particularly for the gases. Shouldn't they be different? Take a look at the unit system. What happened?
They went to liters.
We went to liters. Why did we switch to liters? Because if we didn't switch to liters, what would our density for our gases be?
Not more. Decimal.
Okay. That number is now so small we don't want to manipulate or see that anymore, so we created a new unit to kind of make it easier to manipulate. Does that make sense? Okay. So when we're looking at our numerical values, we have to be very careful to also address the units. The numerical values in and of themselves aren't perfect. Okay. How could we manipulate densities? We got a graduated cylinder, sort of, on the right, with a bunch of stuff in it. Okay, L for liquid, S for solids. What can you tell me about solid number 2? How do you know it's more dense than water? Okay, when I look at the relationship between solid 2 and water, where's the solid? At the bottom of water. Why is it at the bottom? It's not heavier. It's more dense. Okay, it has to do with the density. Okay, because I could look at water in a boat. The boat weighs a lot more than the water. Why does the boat float? It's less dense. We've taken that mass and we spread it out over a large volume so that its density now is less than water. That's why our boats float. Okay, let's take a look at a submarine. What's the whole point of a submarine?
Just sink. No.
Let's be a little bit careful with that.
Submerged.
If our submarines only sunk, that would kind of suck. What's the whole point of a submarine?
To be able to stay underwater at the exact depth that they want.
Go underwater and
Stay there.
stay there and
Go up.
go up. Because if you're only underwater,
But we got a lot of air with you.
yeah, okay. So we need to think of and if you're only underwater, how did you get the people into said submarine? I mean, yeah, don't think too hard on that. Okay? So we do have to get the sub up. Okay? So what does the submarine do? It's constantly moving up and down. How does it move up and down?
It fills ballast tanks with air.
Okay? We can adjust the volume or the mass of that object, the density of it, by either pumping air into the sub, in which case the density changes and it rises. How do we get it to sink?
You empty out the ballast tanks.
Okay, you empty out the ballast tanks, and I'm not positive on this one. What do you fill them with?
You fill it with seawater.
You fill them with seawater. Now what happens?
That means
You sink because the density has risen enough that you can now drop into the water. Okay? By finding a very careful balance between putting water in or air in, we can adjust the volume so that the sub stays at different, not altitude, depths. Depths is right. Yes.
Scuba divers wear the same
Okay.
thing.
And scuba divers do the same thing. Okay? What do? Lead weights?
yeah, they have weights on them, then, but you have a BCD that you fill with air or release air on.
I'll just accept your word for that. I have no idea what BCD is. But there we go. Okay, so you can adjust your density, and that's how we move up and down. It's all about densities. Okay? Kind of makes sense? Cool. So, calculating densities, do you guys want to look at more conversions? No. Okay. This is more density stuff as conversions. Okay. This kind of starts getting to where we're going to need to get. Do you have to have heard of a conversion to be able to use it, or the unit to be able to use it? How many meeks are in 3.4 stops? Anybody know what a stop is? You know what a meek is? No. Useless is a bit of I don't know, was it you who said useless? Who said useless? Okay. Meeks and stops could be very useful, but I have no idea what they are. Okay? And until I know what they are, I may not have a meaning behind them to decide whether they're useful or useless. Could I still go through and do a conversion?
Yeah, because they gave us the conversion.
If you're given a conversion factor, you could go through and convert. Okay? So part of what we did in that last unit was to get you used to how to convert. So that when you move to some weird unit that you don't know how to comprehend, you can still do conversions. The idea being is that when we move to that unit, we can now talk about it enough, and you start to learn and understand why we would use that new unit. But at the same time, you have to be running constantly the conversions, because if we wait for you to understand what the unit means, right, which arguably none of you will, right, you won't be able to do anything with it. Okay, we can't advance through the class. Okay, so what we want is, again, that process so that we can do those conversions. With enough conversions, hopefully the meaning starts to sink in, and we can then start to use it and understand why we're using it. Make sense? Okay, double replacement reactions. Okay, you should be familiar with these. We could go through and predict these out. Oh, who's at the door? Jerks. You're supposed to turn around. Okay. So if we wrote down the given information, we should be able to look at this and see that this does match the general pattern for a double replacement. We would do our double replacement. Potassium needs to partner with chloride. Okay. Barium needs to partner with chromate. That's just the general pattern behind it. Notice that I did not write K2Cl2. Wasn't there a 2 with potassium chromate? Why is the 2 there?
To balance with chromate.
To balance the chromate. Is potassium with chromate anymore?
Yeah.
No, so you can't bring that 2 across. Okay? How do I know if I need a 2 there or not? I have to balance that product. I have to go through and say that potassium is +1. The chloride is -1. Do those balance each other in their current state? Yes, that's now a correct product. Okay? I could go over and do that with the barium chromate as well. Charge on barium +2. Charge on chromate. How do you know it's a -2? I'll accept 2 answers. Memorization is 1. Okay? And those of you will be like, but you didn't tell me to memorize it. You're right. So let's not use memorization. How else would you be able to determine the charge on the chromate?
Because in the reactant side, you needed 2 potassium, and you know what the charge of potassium.
You are required to know that potassium is a +1. If there's 2 potassiums, the chromate must be -2, which means the chromate on the far side is also a -2. Right? So one of the things I told you to do was memorize charges, and those are the most common ones used. Okay? The other ones you could potentially derive in the question. Okay? So, is that a correct formula? Right? 2 barium, 2 chromate? Yes. Okay? Now I could balance the equation. Is the equation balanced? No, because there's not enough potassiums, there's not enough chloride on the product side. So we could fix that by doing what? 2 in front of our potassium chloride. Let's see, did I do that right? No, I didn't do it. So let's put the 2 in there. What else is different in this equation? Anything show up that you're like, hey, where'd that come from? The phases. How do we know those phases? You have to use solubility rules. Okay? So by using the solubility rules, you would find barium chromate is insoluble and always insoluble, which then means its phase is solid. If I move to potassium chloride, using the solubility rules, it is always soluble, which makes it aqueous. Right? So if I looked at these 2 reactions, in both of these cases, you'll notice this bottom one is slightly different. They're all aqueous. Did a chemical reaction happen?
No.
How do you know? Isn't sodium with nitrate versus sodium with chloride? Okay. Your chemical reactions. How do we know there's a chemical reaction? A change in phase, which was already shouted out. Transfer of energy, I'll accept that. That's change in energy. Temperature and energy are the same. Third one.
Light emission.
That's also an energy. State we already got. Really?
Changing.
There we go. Change in color. Okay, of those three, which one's going to be the most useful here? Change in physical state. Can we look at a piece of paper and say temperature changed? No. All you'd be told is temperature changed. And you'd be like, well, that's why I know it changed. Well, I told you that. That doesn't count. Okay, we can't look at a reaction to see that the temperature changed. How about change in color? Can't really see that either. I mean, theoretically, I could print it in color, but that's expensive, and I don't want to do that. Okay, so the only thing you could look for in an exam is change in physical state. Aqueous, aqueous becomes aqueous, aqueous. What does that mean? No chemical reaction. Okay? Just like the single replacements, you should predict your products, look at those phases, and then answer the question, did a chemical reaction happen? For the first one, did a chemical reaction happen?
Yes.
Yes, because change in state. For the second one, did a chemical reaction happen?
No.
No. Okay? So you could be asked, predict the products of that second one. Okay? And one of your answers could very well be what do you think NR is? No reaction. Okay, so it could very well mean that. Did I have to go through and predict those products? It gets kind of borderline. If you're good at being able to do those swaps in your head to hold on to what those structures were so that you could then use the solubility rules, then fine, you could do it in your head. Okay? Your head is a scary, scary place to be. Write it down. When it's written down, now you can look at it and say whether it was a reaction or not. Yes?
I have a question about temperature change with chemical reactions. If the temperature changes, is it going to stay that temperature forever until something else happens, or would it eventually go back down to a different temperature after an amount of time?
So let's use a potentially weird example of this. Let's use an alternate definition of the word hot. You can think of someone that is hot, right? Person that is hot. Everybody can do that, right? And stop freaking looking at me. It's really creepy. Okay. So you've got an idea of someone that is hot. Are they going to be hot always? You're like, oh, of course they will. In 100 years from now, let's make it 200 years from now, are they still going to be hot? They're probably going to be a little pile of dirt. Okay, if we're going to be nice to them. More than likely, they're probably a rotting skeleton in 200 years. Pretty sure that may be a whole other issue. Okay? They're not hot anymore. Okay? So if a temperature changes, will the temperature still fluctuate after the chemical reaction?
Yes.
Yes, because what is that chemical reaction in? In the room. Is the temperature of the room controlled? Yes. Which means once the chemical reaction has stopped producing heat, there's no more heat generated. That container can't stay hot, because eventually what's the container going to do? Transfer the heat to the room, and then the room will cool down. So you will never get a constant, once the temperature is changed, it's not going to stay changed forever. It will eventually drop back down.
But the chemicals are still together.
But the chemicals have still happened. So the chemical change produces a heat. Bing! There's the heat. Okay, where does that heat then go? Okay, it goes out. Okay, if we're there to monitor, whoop, the temperature came out, now I can monitor that change in heat. What if I'm not there to monitor that change in heat? Did it still release that energy? Does a bear? No, that's the wrong one. The tree falls in a wood, not a bear. That's a bad analogy. Okay, a tree falls in the wood. Does it still make sound? Okay, yeah, that temperature is released, and yes, a new chemical bond has happened, but it stopped producing that energy. It's only in the transition from reactants to products the energy comes out. Okay, it's not in the new state constantly emitting. Does that make sense?
Is there anything that does that?
There are certain reactions that take longer
Yeah.
and.
There are certain reactions that take longer, so that you might go through and say, like radiation. If I left this species here, it feels like it's going to constantly radiate that energy.
But it's
Okay,
not
like
on time.
Chernobyl. There's the blob. They've got a name for it. There's a space in Chernobyl that you can't go near. The last thing to take an image of, you can look pictures for it. The elephant foot? There we go. The elephant's foot. Okay. The only way they could get a picture of it, because the amount of energy coming off of it, was to use multiple mirrors, and it still destroyed the robot that was taking the picture of it. Okay. And you might say, well, isn't that constantly emitting energy?
It'll die.
It'll eventually die off. Within the time frame that we're looking at, we aren't going to see it. So it depends on how long your time frame is. Another answer that could be provided for this question, okay, I could easily just write this is a product. Okay, that gets a little bit weird, because is that a product? No. Okay, really what we're saying is that I mix these two things, what's left in the beaker? The same thing that I started with. Okay? I'm showing that no reaction happened. Does that make sense? Okay, so solubility rules. Okay, there's a big list of them. You're expected to use them like you did on the exam. Okay?
We'll always have those on the test.
I will always give you those for my exams.
Oh, God.
I don't write the final. Okay. We're in debates about that. We're in debates about that now, and we'll see what comes out of that. And I'll let you know as soon as I know.
Debate well.
Okay. I've won some arguments, and I've lost lots of arguments too. Right. So I expect you to go through and use them. Some of these I have memorized. Okay. Any guesses as to which of these I've got memorized? I've actually only memorized 3 of them. 1, 2, 3. Why did I only memorize 1, 2, 3? I don't accept easy, I don't accept common. Most likely it goes back to most common. Look at rule number 4. 5, 6, 7, 8, 9, okay, 10. Okay, why did I memorize the first 3? There are no exceptions. Okay, so with that, I can whittle down a lot of answers with just those 3. After that, I may have to go out and look stuff up. Okay, make sense? So I tell you to memorize things for a reason. Generally, the reason is because there are no exceptions. Okay, or it is an exception. Okay? Too many have exceptions, so it doesn't make sense to memorize those. Neutralizations, same thing as a double replacement. Okay? The biggest and most important aspect to get out of the neutralization, though, is that it is specifically referencing what species? HAQ, we're looking at an acid. Okay? That officially is the only one we know right now. We'll look at the base definition later. Okay? But neutralizations are the reaction of an acid and a base. What do acids and bases always produce?
Water.
Always water and a salt. Okay? You will see me write out water is HOH. Why? Okay. It's easier for me to see the double replacement. Okay? You don't want to write out HOH, that's fine. I don't care. Okay? In fact, when I was teaching Gen Chem stuff, and I always wrote out H2O. And I was like, why would you ever write it out any other way? Because it's H2O, it's not HOH. And somebody was like, but I can see it better. And I was like, okay, you're right. I'll write it as HOH. And I've been doing so since then. Okay? It can help you differentiate those things and allow you to balance without having to look at elements. Make sense? Okay. So there's a reaction we could look at, but we're just going to skip it. The reaction type with combustions, really all you have to do is be able to recognize them. Okay? The balancing of them can be hard. We looked at the balancing of this one in particular they can be a lot more difficult to go through and balance because you end up with those half things. The biggest reason why they're difficult to balance, oxygen. Oxygen is showing up in two places at the same time, okay, on one side of the equation. Any element that shows up in multiple places on the same side of an equation is a difficult element to balance, right? And it should almost always be left for last. Oxygen is the most common one to do that because it is very abundant and very reactive, okay? Which means because of its abundance, it can show up in a lot of different places. Because it is reactive, it will react in all of those places. Okay? So as a general rule, if you go back and look at our guidelines for balancing chemical reactions, I usually say to leave one element for the end. Oxygen. Okay? And it's for that very reason. Okay? Temperature. This is some new-ish stuff. Temperature is a measure of the average kinetic energy for an individual sample. Okay, which is a really fancy way of just being confusing. Okay? But we'll look at an example why in a second. Okay? We get 3 temperature scales. Why do we have multiple temperature scales?
Because we have multiple people.
Why would multiple people have discovered temperature?
Different times.
How common is temperature? When you step outside in Arizona, you typically go, oh, it's hot. Okay, I want to be able to tell people in the other place of the world that it's hot. Okay, well, they're like, well, how hot is it? Because it's really hot where I am, you know, in the Mediterranean. Geez, it's 90 degrees. This is awful. 90 degrees, that's like awesome. What's wrong with you? That's not hot. Okay? We need to have a way to compare that. That's why we quantify. Temperature is or the measure of the average kinetic energy for anything we observe is such a common phenomenon to observe that we come up with ways to quantify it. So we have Fahrenheit, Celsius, and Kelvin. They were all discovered at differing stages through our history. We get fights between Fahrenheit and Celsius early on. Science came through later with Kelvin. Once we had a better understanding, ultimately, of physics and energy, we invent Kelvin. So depending on where you are in the world and what system you're looking at, you may use different temperature scales. Okay? Common readings that come off of them, and there's reasons behind why each of these systems exist, even though some of them seem completely nonsensical. Freezing point for water might make sense. Okay, I want where water stops moving. Okay, why would I pick 32 degrees? And that's when it stops moving. Celsius picked 0. Why did Fahrenheit pick 32?
Because it wanted to be difficult.
It wanted to be difficult.
Now they came up with their system before, I don't know.
Or they could actually freeze water.
Are there things colder than just ice?
Yes.
Yes. So the things that they could measure that were colder than ice, they set at 0. Okay? So that's why Fahrenheit is at 32 for the freezing point of water. Why is Celsius at 0? Well, because when they first looked at it, they looked at the freezing point of water. There's a 0 point. So depending on where you establish your scale, you're going to get different numbers. There's a reason and a logic behind those numbers. Okay? We don't necessarily see that. Okay? Because we now have 2 different systems, what do we have to do? Convert between them. And so somebody had to do all that fun math to deal with that conversion, and we'll look at that in a second. Kelvin came along and noticed that there's a lot of temperatures below 0 degrees Celsius or below 32 degrees Fahrenheit. Okay? We said, well, I wonder if there's an absolute point. Okay? And if we go through motion and energy enough, we do define an absolute point. The absolute point is 0 degree or 0 Kelvin. So there's a place where all energy stops. That's 0 Kelvin. All right? If we look at our common temperatures, we get the freezing point for water at 273. It's a good thing I fixed that typo, didn't I? Degrees Celsius. What am I doing? Oh, no, sorry, I recognize the typo now. K looked like F to me. There is a small typo there. What did I just fix? The degrees. Kelvin is in a degree scale. Okay, they're absolutes, so there's no degrees there. There are degrees for Celsius and Fahrenheit. Subtle difference. Okay? Again, the numbers seem weird, but again, you have to have the context behind where those systems came from. You need more physics and probably quantum to be able to understand where those scales came from. Okay? So conversions, if I want to go from Celsius into Fahrenheit, this is what I have to go through and use. Does that look complicated and weird? Yeah, I completely agree. Okay? I could also go through and do Fahrenheit to Celsius. Okay? Does that look weird? Yep, I would argue that looks even weirder than that one, but that's because of the algebra to shift everything around. Okay? Celsius to Kelvin, that's a kind of nice one. You just add 273. Notice it says 273.15. Everybody goes, where'd you get the 1.5? I memorized it. Why? I don't know. It's just stuck. It has a nice ring to it, 273.15. Right? What are you responsible for memorizing? 273. Because 273 has how many sig figs? 3. And typically when we're doing sig fig conversions, we stick with 3 sig figs. So all you're responsible is for 273. Okay? You want to add the 0.15? Cool, you look now extra intelligent. Okay, we all do this. Everybody's like, no, and I don't try and make myself look intelligent. Shut up, you do. Okay? This is my time. That's my time. There's my, I'm extra intelligent. I memorized 2 extra decimal places. Okay? You got to give me something. Okay? I expect you to memorize that one. 273 for Celsius to Kelvin. These other ones, I haven't memorized. So guess what I do? I give them to you. They're on your exam. Okay? And I only give you one of them. Why do I not give you the other? You can figure it out. Okay? That's the algebra part of the math class that you should be able to go through and do. Okay? You want to do some conversions? Yeah? Okay. Body temperature is 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius and in Kelvin? Through? So I just happen to memorize this because I've solved it enough times. Okay, so degrees Celsius. Notice in this case that what I give you on the exam is the degree Celsius to Fahrenheit, and yet what am I asking you to solve for? The reverse one. Okay, you can fully expect that to show up that way on the test. So what you could just go through and do is just plug stuff in. Whoops, not 37, because we're solving for that. Degrees Celsius, 9 over 5, was it plus 32? Equals our Fahrenheit. Our Fahrenheit was 98.6. I'll rearrange things to solve for degrees Celsius. 98.6 minus 32 times 5 over 9. Yeah? Punch that into the calculator. Theoretically, you get 37. A couple people said they got exactly 37. So is my answer correct in black? No. It is wrong. Why is it wrong? Sig figs. The information given was in 3 sig figs. I need an extra decimal. 37.0
And the rest of the
degrees
ones that are
Celsius.
smaller, it doesn't matter because it's conversion, right?
Yeah, we're taking, and it could be a very questionable assumption, but we're making the assumption that the rest of those numbers were exact. Okay. How do we convert to Kelvin? My Kelvin is 37 plus 273, and I get whatever that answer was. I can't, 310. Yeah. Actually, decimal, decimal point. Kelvin. Yeah? Why do I need the decimal point?
Because if you didn't, it'd only have 2 sig figs.
I'd lose sig figs, right? Because that's officially 37.0. Make sense?
Do you have to put a 0 after the decimal point, or you just put it off?
For where?
So you don't have to put an extra zero, because then it would be.
For which one?
For the
That one that
310
just-
Kelvin.
The 310 Kelvin.
Yeah. You
For-
don't have to put an extra zero, because then it would be 4 sig.
True. I do not want an extra zero there because that's now 4 sig figs.
You can just put the decimal point.
All I would need is the decimal point. Okay. If I wanted to be extra clear, how can it be extra clear? 3.10 times 10 to the second kelvins. Okay? Yay, all that old stuff. Okay. Heat. So temperature measured the average energy. Heat is a measure of the total energy. Right? And this is kind of a hard concept to get until we try and make an example of it. Right? I take a drop of coffee. Right? It's hot coffee. So 100 degrees Celsius. Right? We're 98 degrees Celsius, otherwise it's a gas, right? Okay, so 98 degrees Celsius. Okay, that's really hot, right? Right? And I take a cup of coffee, same temperature, 98 degrees Celsius. One of those gets splashed on you. Which one are you concerned about? Why are you concerned about the cup? They're both at the exact same temperature.
Because that drop is more likely to cool before it hits you.
Nope.
No.
The instant it touches your skin, it is at 98 degrees Celsius. So I disagree with the cooling part. It's not a bad idea. There's a lot more in the cup. What do you mean? I actually don't really care about the liquid. What do I care about?
More energy.
I care about the energy. I care about the heat. The heat is the total energy. Every single one of the particles in both the drop and the cup have that energy associated with them. Okay? If it's a drop, I'm only getting hit with, it's not 5 particles, but let's just say 5 particles at 98 degrees Celsius. That might sting a little bit, but it's probably not that bad. If I take the cup, instead of it being 5 particles, it's now 5 million particles. Every single one of those particles is now going to transfer that heat into my skin. That's a lot more energy for me to absorb. Okay? That's going to be the pain, which could now be a lawsuit. Right? Kind of make sense? So heat is total energy, all the energy in the system. Temperature is just the average energy. Kind of make sense? Okay. Specific heat now relates to an individual substance. Okay? Don't stress about this number or necessarily the units of it, though you've already used it in one of your labs. Right? What the specific heat is a property, a physical property for a material. Right? And what that number represents is the amount of energy I have to put in. So energy measured in calories or joules, which are just energy terms, or energy units. The amount of energy I have to put in to cause 1 gram of a substance to go up by 1 degree Celsius. Right? So if I look at kind of the easier one, come on. The calorie unit, I have to add 1 calorie of energy in to 1 gram of water to make it go up by 1 degree Celsius. Okay? That's actually why that unit was invented of calories, because it's all ones. Okay? What if I change the substance? Okay? Let's make it air. How much energy would I have to put into air to make the temperature go up by 1 degree Celsius? Do you think I'd have to add more energy or less energy? Less energy. Right? If I have to add less energy in, what happens to the specific heat? It's still 1 gram, it's still 1 degree Celsius, but I'm now putting a smaller energy in. What happens to my specific heat? It goes down. So what I can do is go through and look at specific heats for different materials to try and come up with their relationships. And that's what I primarily want you to focus on. I don't want to deal with the conversions on it. If you move into 151, you can do conversions then. Have fun. Okay? So let's look at an exam question. Which of the following substances is expected to have the largest specific heat? Whoa. Okay, so we got a lot of things going on with this. Okay? One interesting option is at least one person in the room immediately looked to the periodic table, which is a good thing to do. Okay, so since we're starting there, can I look to the periodic table to find copper? Everybody's saying yes. Where does it say copper on the periodic table? It doesn't specifically say copper. So this multiple choice question is actually getting at multiple different things. The first thing it's getting at is, did you remember the symbols for your individual elements? Okay? So when you look to the periodic table, and a lot of people shouted it out, which is good, copper is actually Cu. What else would I need to simplify here? Carbon down to just C. Okay, cool. So they're now all in the same representation, and I could use the periodic table to look for this. Well, what am I looking for? Okay, that's now going to go back to what this largest specific heat means. Okay, if I have a large specific heat, how much energy do I have to put in? Okay. What would be a larger specific heat than 1 calorie per gram degree Celsius? Okay. 2, touche. Let's be a little bit more larger. Man, you guys are. Okay, let's go all out. 1,000 calories per gram degree Celsius. So what I'm saying is I have to add in 1,000 calories of energy into the system to make 1 gram go up by 1 degree Celsius. I have to put a lot of energy in, right? Okay. Why is the substance not going up with temperature?
Larger mass.
Can't be a larger mass because it is
1 gram.
1 gram.
Higher density.
So something about that material requires lots of energy to go into it before it actually absorbs the energy or allows us to monitor it. What might you describe that material to be? Okay. Let's take a look at a pot. Put a pot on the stove. I turn on the stove. I now touch the pot. How many people have done that? Yeah, it sucks, doesn't it? Yeah, don't do that. It hurts. Okay. But if I put, say, a hot pad on the stove and did the same thing, turned it on, and I touched the hot pad, would that hurt? No. Why not? What is the difference between the hot pad and the pot? One is a conductor of heat, which means when I add heat to it, what does the heat do? It goes directly through it. It changes the temperature very, very quickly. The insulator, instead, absorbs the heat and doesn't change the temperature. Okay, so I have to add a lot of heat into the insulator to get the temperature to go up. So if I have a large specific heat, what am I referencing? What kind of compound? A conductor? A conductor or an insulator? An insulator. Okay, so we're looking at an insulator versus a conductor. That says conductor, just trust me. I was going to cross it out anyway. Okay. Do I know something about the materials on the periodic table that would allow me to tell the difference between insulators and conductors of heat? Yeah. Metals conduct heat. But metals are conductors, and conductors is not what I want. Which means more than likely I'm looking for a nonmetal. How do I tell the difference between metals and nonmetals? The staircase. To the left of the staircase is metal. To the right of the staircase, nonmetal. Where's calcium? To the left. Chromium. Copper. Sorry. Thinking of something. PB. Yeah. And I couldn't figure out how to make sense of it. C. To the right. Which means there's our answer. So really all this question is asking is which one of these is a nonmetal? That's a really easy question, right? Right? But if we get to the properties that allow us to differentiate these, it now becomes a harder question that we have to think a little bit more about, and you have to recognize all of those steps. Yes?
If it's two non-metals, how would you tell which?
Could you expect me to do something like this?
You next.
You guys are jerks. No, I would never ask that question. Okay? Ultimately, because this relationship of our specific heats is not perfect. Okay? So the other thing we can do is switch this to smallest specific heat. With those answer choices, I would not expect you to be able to answer the smallest specific heat, because the smallest specific heat should be the metal. There's a lot of metals on there. How would you differentiate? Okay? So within those groups, those categories, there are exceptions, there are variations. Okay? That's why when I go through to build this question, I'm very careful about which elements I pick to make sure that it guarantees only one. How would I make sure to guarantee it?
Only have one non-metal?
Or what?
I look up the specific heats, okay, to make sure that it matches the trend. Does that make sense? Okay. Conservation of mass. Okay. When we run a chemical reaction, okay, we can't create or destroy matter. And we've kind of talked about this is why balancing works. Okay. But when we looked at it as balancing, we looked at individual elements. We can't destroy elements. This is now more general in saying I can't destroy mass. So if I start with, and for those of you good at math in the next section, hold your tongue. 2 grams of hydrogen and 8 grams of oxygen, and it completely all becomes water, what would the mass of the water be? 10 grams. Okay, because I can't create or destroy matter, all of it must be produced. Okay, what if I went through and I said 2 grams of wood and 8 grams of oxygen? How many grams of gas are produced? Okay, well I heard an issue 8, then how much water was produced? 2. Couldn't I have been 5 and 5? Okay, or 9 and 1, or 1 and 9. Okay, or if we're going to get really nasty, 2.5 and 7.5. Don't all of those satisfy that balance? Yes. So if I only give you, well, that took a long time to erase all that, sorry. That information at the, oh man. That information at the bottom. 2 grams of wood, 8 grams of oxygen. Can you tell me how much gas was produced? No. To figure out how much gas was produced, what else do you need to know?
How much water was produced?
You would also need to know how much water was produced. Once you know that, how much gas was produced? 6 grams. Everybody get that? Okay. So our conservation of mass works out great for combination reactions or decompositions. Okay? Because we either start with one decomposition or we end with one combination. Okay? But if there's multiple things on both sides, we have to be provided more mass. Okay? There are other ways to go through and solve, so ultimately our law of conservation of mass fairly quickly disappears and becomes irrelevant when we move into the next unit with moles. Okay? Law of conservation of mass, energy. This guy, famous guy, said energy and mass are the same thing, okay, or related. So if I can't destroy mass, what does that also mean? I can't destroy energy. So I can transfer energy from one place to another, but I can't destroy it. Okay? This comes in important for us. Okay? If I want to boil water, what do I have to do? Apply heat to it. Where did I get the heat from? The stove. What's in the stove?
Electricity or gas.
Electricity or gas. If we pick gas, where's the heat coming from?
Gas being on fire.
A chemical reaction. The gas combusting. That combustion reaction produces heat. I funnel all that heat to go where?
The metal of the pan.
Into the metal of the pan. What does the metal of the pan do?
Transfer the heat.
Transfers the heat to the water, which then causes the water to heat up. Why did I boil water?
To make spaghetti.
Okay, to make spaghetti. Okay, so now that high energy water can get forced into my food, so now my food isn't just little crispy bites of spaghetti. Okay, so what we're looking at is the energy forms and how they can transition from one place to another. There are 6 primary categories for energy. We'll pick up with that when we return next week.